What am I up to today? Well, I've been shopping at my local J-Car shop and bought a number of bits and pieces. And you might ask, what am I up to? Well, there's been a Chinese company that's been nagging me for ages to try out their PCB manufacturing service. And if you're not familiar with the acronym, it's printed circuit board, and not the really horribly destructive and poisonous oils that are used in transformers. So I've already requested a board to be manufactured, and it's actually been manufactured and shipped faster than an Australian manufacturer could even get back to my quote. As it turns out, the Australian manufacturer pretty much drop ships from the Chinese manufacturer, which turns out to be the same place that I've ordered mine from. So I don't feel so guilty about not ordering in the country because of that. Now, the first design that I've ordered is a little test board that's used for these video ballons that I've been using for AHD cameras to run down Cat5. And as a result of some of the people that I've been working with not strictly being careful about how they wire the Cat5 plugs, we've had a few little issues. So I've designed a little tester unit, which you'll see in another video. But enough about that for the moment. Today what I'm making is a 12 volt uninterruptible power supply. And the design, or the purpose of this here, is to allow me to run a 12 volt device off two different supplies. Namely something like a wall wart or a plug pack, whichever terminology you prefer, to supply 12 volts and a battery backup. The initial situation that inspired this was me wanting to have a solar powered camera system that can be, you can walk up and plug in a main supply to augment that without having to interrupt or reset the camera system. Whereas I couldn't find very many products like this, and the only one that I have found was suggested to me by my local J-Car guy, and he said it's built into a plug pack, which doesn't really suit what I need. I needed a separate unit. I'm using the 5.5, 2.5, or 5.5, 2.1 mil DC jacks, and I've actually put 5.5, 2.5 on here, which is actually wrong. I'll amend that later. So yeah, basically let's have a look at the board design. So I've gone all out and used the free Design Spark software here and had it auto route the nets, and then manually done some adjustment here. I was going to use a copper paw, but you know, I figured that was just going to be a pain in the ass, especially considering I made some track changes from my original schematic. I decided I had some real fundamental problems. And that was with the help of my senior designer here, of which there is some of his notes here, which are, this was the original schematic, not as easily readable, but we noticed I had some connections right here where I had positive and negative connecting at that junction there. That would have been a little catastrophic. But yes, we've done a bit of maths about the capacitor loadings and whatnot. So this is just giving you a quick look. Let's actually have a look at the schematic up close. Okay, so let's take a close look here. Now, this is not probably the easiest to read schematic because I've used Design Spark's components. But these are 5.5, 2.1 mil sockets, and you might notice I've written 2.5 here. That's an oversight on my part. Most of the systems I'm designing this for use 2.1 millimeter pins, namely CCTV stuff. So let's have a look here. This is our backup input. This is our main input socket, and over here is our output socket. So what's happening here is our main input socket is feeding power to the coils on a relay, preferably a solid state relay. We have a diode here which is for flyback protection, and an itty bitty little capacitor here, which actually turns out I'm using something smaller than a 1 microfarad. The purpose of this is basically to absorb the flyback spike long enough for the diode to begin conducting. And the diode here is just a 1N4004. I'm probably going to a 4007 just for the higher voltage. That should hopefully absorb the spike. If I'm using a solid state relay as intended, that's probably a lot less important. And yes, I know most people, I should probably put a resistor in here as well. It's not the most ideal flyback protection, but I needed to keep the board small. Off the side here is a current limiting resistor and an LED, basically just to tell me that there's power on the main socket. Some more observant of you will probably notice that there's no LED on the battery backup. That's simply because I wanted it completely isolated with no current drain, in case it was like a primary cell battery or something like that. Now, there is an LED again on the output to signify that things are running, with a 390 ohm resistor and a standard little 5mm LED. That just drops the current, if I remember off the top of my head, to about 15 or 20 milliamps, somewhere around there, maybe 30. I did the maths so long ago, I've just got used to using a 390 ohm resistor in series. Now, on the output side here, it's actually pretty simple. There's a diode here to prevent bleed back, and there's a big fat, this says 3000 mic. I found that a preferred value is actually 4700, so that's what I'm using. This is an electrolytic capacitor. It's designed to run the total output load long enough for the 5 or 10 milliseconds or so it takes the relay contacts to shut. And it's so big because I'm expecting to run maybe a 1 amp load on this. I could end up using this for my VDSL modem, because in case you're not aware, Australia is going to this crazy thing called NBN, and we don't really have an option. So they're using VDSL and copper to the node, which is stupid idea. Well, but I'll rant in that in a different video. Now, the tricky bit on how this works is actually not that tricky. I have the common output of the relay, which is just a single pole relay. The common feeds my output. The normally open, which will be closed when powered, is fed from the main input. So the moment you hook power up, it closes the relay and connects to this. If, for instance, or in the situation where main power is lost, the relay will drop, the capacitor will carry the load, and then the normally closed contact will then switch the battery line in here. So not a particularly complicated circuit, and something I need to test first. And that's where the experimenter's kit comes in, that's way out of focus here. So, contrary to my usual behavior, I decided to actually test something before commencing building it. Probably because I'm going to be doing a little bit more of this. So I bought an Arduino, or however you pronounce that. Somebody might correct me there. This is called a Arduino Tech Experimenter's Kit. I bought it purely because it has a solderless breadboard in the kit, and it was on special. And they didn't have any just plain breadboards on the shelf. In either case, I'll use pretty much every part of this kit at some point. So we'll get that open. I also brought enough parts to manufacture 2 test units, and I bought some solder type breadboard as well. So I couldn't find solid state relays on the shelf, so I ended up with just some standard. I've got a 3 amp and a 10 amp relay with a conventional coil type with the same footprint as what I'm planning to use. Because this kit will be nicely, I've tried to design it to use standard through-hole parts and easily substituted values. And probably the most expensive part of the whole thing, aside from the relay, are these big fat capacitors. But we really want to make sure that it carries that load. In the event of a power outage, nobody wants their modem resetting or their cameras dropping out, because it could mean that somebody could sit there and conceivably flick the power on and off at a switchboard and interrupt the cameras until they die completely, or the hard drive's corrupted. Either case, that's something we don't want. We want to make this idiot proof. So I'm going to go and take this breadboard out of the box and see what we can do with it. So let's get my trusty Leatherman on the job. And for those of you who wonder what Leatherman I'm using, I use a rebar, which I'm happy to say that when I did something profoundly stupid a couple of years back and snapped the tips off both the blades, they actually did honour their 10-year warranty or whatever they do and sent me a completely new one rather than fix it. In contrast, I also carry a Victorinox Cyber tool. which, believe it or not, used to be a Swiss Flame. And 11 years after I bought it, the cigarette lighter component of the Swiss Flame blew up. The hose perished. I found out that was a congenital problem and they no longer produced them anymore. So when I contacted Victorinox, they sent me out this as a replacement to honour their lifetime warranty. So guys, it really pays off to buy quality tools. It really, really does. So let's pull this aside. Let's get into this Arduino Tech thingy. And you're probably poking at my Aussie accent. So there's our Arduino unit. We don't need to know about that for now. There's some sort of breakout board, which will be interesting. We don't care about any of that stuff. USB lead. Well, I didn't have to buy LEDs. I should have just used these, but some pretty looking blue ones. I might use them later. An adjustment pot. That might actually be handy for playing with some resistances. And there's my breadboard. That's what we want. And it looks like I've got a whole bunch of pre-terminated links. That will be handy. So I guess what I've got to do now is translate my schematic into a breadboard diagram and place some components. So I think I'll do that off camera because you probably don't want to hear all the profanities I'm going to yell at this when I get confused. So I'd rather look like I know what I'm doing. So let's jump straight to that bit about now. What the hell is going on with this? So after deciding that the relay wouldn't really fit into the breadboard, I soldered some breadboard connectors to the relay. So I can use solder to fit a relay to a solderless breadboard. Interesting. Anyway, time to start plugging everything together. Okay, so we're sort of halfway to having it assembled. So I'll just explain what's going on here before I hook the power up and let the magic smoke out. So we have our power rails here. This is our power input, using some of that nice silicon cable I showed in a different video. Excuse me while I clear my throat. This is our tiny little, probably superfluous capacitor that might not be necessary. This is a 1N4004 diode. This is for flyback. Our relay coils are these two white ones here, and they're hooked across the power rail as well. And the normally open contact on this yellow wire is hooked to the positive there. This is just the normally closed contact that just shoved over here to get it out of the way. The green wire here is the outcoming. Geez, I have a dry throat tonight. This is the common from the relay going through a bleed back diode or anti-bleed back diode, jumping over to the positive rail to which we have our 4700 mic cap on. Now what I'm trying to work at here is to make sure that when we energize the relay, when the power is removed, this capacitor doesn't continue to run the relay coils, as has happened in previous experiments. So let's just go and flick our power on. So I can hear the relay clicking, and it's clicking on and off. It's not bleeding back through. So the experiment here would be to see if I go across to this. Now actually it does occur to me that I actually don't have a common ground link here, so I probably need to find a little black jumper lead here, and because I'm going to be running a common ground across all of this, I'll connect the ground rails together. Now my lights flicked for a minute, which tells me the capacitor charged up, and you can probably hear from the sound my relay is clicking on and off nicely without actually bleeding back into that. The difference in that would be if I jump this over to here. And you can hear when that runs, when I turn the switch off, the relay has a slight delay, which for my purposes would be a problem. So that little principle of that diode being in there is going to work just right. So let's assemble the rest of this and probably shut my soundproof door so you don't hear all the background noise. So I've made a couple of changes here, one of which is this is an output indicator LED and this is an input indicator. It shows the input current. I'm going to turn off the overhead light so that you can see this. Let's turn power on. We can see there's power coming in, power coming out. That's great. If we turn power off, we can see the capacitor continues to feed this whilst the relay turns off. Now there's a very, very little current through there, but that is bleeding entirely off the capacitor, which is what we would expect, and it's not bleeding back through the relay, which is very nice. That's exactly what we want to see. So let's move on to the next bit. Okay, so this is about the third time I've had to film this because of various interruptions. This here is a 12 volt 7.2 amp hour sealed lead acid battery that I obtained from my local JCar store, like I do most things. That is now connected to this circuit, and for the observant among you, you'll notice there is now this third light. So this is our mains input, this is our output, and this is our battery input. So what we're going to do is light our battery input and turn our overhead lights off. You can now see that our battery input is being passed through to our output. If we then turn on main supply, it comes on, and the load should be disconnected from that. Importantly, there was no interruption to this little guy. If I then turn off the main supply, the output remains uninterrupted, hence uninterrupted power supply, or UPS. So the proof of concept is going to work quite well. The only other thing to do now is to test it with a load. So I need to find something with about a 1/2 amp load that can indicate to me if it's been reset. I'll have a look around my workshop with the lights on and see what we can find. Okay, well, I found something that should provide a suitable load. This is my little Raspberry Pi in a reversing monitor kit. And crucially, I've put lots of buffering in this, and it's running off a little linear regulator here, and also has a bridge rectifier in there as well. So this should be relatively sensitive to spikes and whatnot. So let's see if I switch over here, and I now switch off my main supply, and it didn't miss a beat. Our main supply has gone on. Let's turn back on, and it switches over without a problem. So let's just make sure that nothing crazy is going on here. I'm going to switch this off, and then I'm going to pull the battery off, and we'll see it go off. We should be able to turn back on using battery, and during boot flick the power over. And I know for a fact this draws around about 800 milliamps, which is not too bad, given that I've got a few other things and there's some loss in the LM7805 on the back. So I think I've got a working proof of concept. This is very, very promising, and to be honest, I probably don't need to build the prototype board one, but I'm going to anyway. So meanwhile, my apprentice is still trashing the office in the background here, but we do have a working prototype. I have decided not to bother soldering it into the prototype board, as I'm fairly confident that my design works. And being as I have a PCB already planned out, the time has come to send off and get that done. And my payday is tomorrow, so that'll probably be when that happens. For now, this is the end of the video until those boards arrive, and in the meantime I'm going to have some other circuit boards arrive, so this stuff will probably greet you a little out of sequence. In any case, I hope this has been some sort of interest to you. It certainly has been for me. I'm kind of excited that this design actually works. As simple as it is, it's something I've been trying to do for a very long time, and now I actually have access to the materials to do it. So yep, I'll give you a thumbs up, out of focus here, and hopefully we'll see this working in progress very soon.